In its simplest form, volume exclusion states the following, that you either have a small particle that you are trying to insert into a volume which contains an available volume. This is the blue part. In which case, the black molecules that already fill the region have intermolecular spaces, and that's where your tiny molecule is likely to fit in. Now, on the other hand, uh, if the excluded volume by the molecules themselves are a certain radius beyond their own sizes, like in this case, the molecule that can be added needs to be smaller, and a comparable sized molecule in that sense becomes almost impossible to add. So in a way, you have a size selection. You see, that was the question we asked, right? How do you get size sieving? Well, tiny molecules can go in, large molecules experience an excluded volume due to sizes of molecular sizes and their interaction radii, and prevent things from getting in. This is a paper by Minton from 2001. Yeah, right. So the volume available by definition then uh, becomes the volume available to species I and its ratio to the total volume. And this is in some senses telling us, in some senses, the volume available, whether the as the molecule's volume increases that you need to add, this number goes on uh, to 1 potentially, and tells you about the so-called possibility of adding something in. So coming back again to hemoglobin concentration um, and the osmotic pressure, this graph essentially demonstrates increasing effective concentration and the role of hemoglobin on osmotic pressure. But what does volume exclusion actually do? So it turns out that it can actually exert forces. And this is quite interesting because so far we've talked about entropic forces, we've talked about electrostatic forces in the passing with the Lennard-Jones potential. We've talked about forces that come out of mechanical properties. These are a very strange set of forces. They're exclusion, volume exclusion forces, almost magical, right? So the idea is the following. If you have a large molecule and a small molecule in a structure, we can simplify them as the big blob, big circle, and the small circle. Then in a dilute system, they don't really interact with each other. There's not much of an effect that we can observe. But if we now increase the small molecules in a large amount, then what we appear to find is that the large molecules, assuming that there's more than just one of them in the system, are more likely to aggregate together. The second example demonstrates that two rod-like solutions, molecules in a solution, are more likely to come together due to so-called depletion forces. And these excluded volume interactions can be treated geometrically to arrive at an exact answer about the extent to which they act and when do they act. So we consider R capital to be the radius of the large disk, R small to be the radius of the small disk in a two-dimensional geometry, and Z as the distance between the large disk and the surface being this solid line here. Right? In such a case, and I asked this rhetorical question earlier, where does this volume exclusion force arise? It's finally nothing but entropy. So we can go back and ask, if there are no conventional forces, like we were saying earlier, van der Waals, electrostatic, etc., the free energy by entropy change alone, due to excluded volume, G excluded, is given by this expression, which looks a little complex. So let's break it down. The first part is the negative term with the number of small molecule particles n capital times kBt, which is your familiar scaling factor, times the natural log of the box volume, the volume we're studying, minus the excluded volume that is lost due to the presence of small molecule particles, and it is plus the original box volume relative to the volume of a unit cell, number of units. You may say omega in the brackets on the right hand side. Yeah. So given this, when the excluded volume is much smaller than the box volume, we can approximate ln 1 plus x to approximately x, and we end up so that ln in the brackets vx by v box becomes this, 1 minus, sorry, vx by v box becomes this. So the g excluded becomes n kBt vx by v box. This is how we got it. Yeah. If two large particles overlap, the excluded volume increases the entropy of the small particle. N times kBt upon V box is the approximate ideal gas osmotic pressure of small particles in a box. So volume exclusion works in some senses by changing the number of possible combinations by which we can arrange things. So the Z term, the Zustandssumme of excluded volume interactions with n particles included is omega factorial upon n minus omega n into omega minus n factorial. Whereas which of course can simplify to omega to the power n upon factorial n. The free energy for excluded volume then becomes G is minus kBt times natural log of Z, and Z next we said, yeah, sorry, I was here. And using Stirling's approximation and assuming the omega, the number of lattice sites is much greater than n, which means again the dilute limit, which is a little ironic because we're considering crowding. But the arithmetic works. 1 minus n upon omega to the power omega is approximately e to the power n, and that simplifies the whole expression of the excluded volume Zustandssumme and the difference in free energies to be approximately 1 upon n minus omega to the power n. The second part, which I mentioned earlier, namely depletion interactions, concern when two large spherical particles are coming together. We determine something like an excluded volume, and this can be based on two large spheres of the same radius and a small sphere of radius small r. Excluded volume has the radius r capital plus r small. Sorry, I think this small sphere radius should actually read the exclusion volume radius. Yeah, the overlap volume from the spherical caps is the cone minus volume of the cone, the spherical cone minus the volume of the cone, this little part here. And so volume and depletion, so the depletion interactions can be got at by combining volumes and forces to tell us that the total excluded volume is V excluded in geometric terms, 4 by 3 pi r cube, r being the r plus r cube, r capital plus r, that is the radius of the particle plus the radius of the excluded volume minus V overlap. And the spherical cone then in fact its volume becomes 2 by 3 times pi r square times r plus r minus d by 2, and d, if you remember, is the distance between the two particles. Volume cone then is sort of simplifies, and then the overlap simplifies, and this is a bit of arithmetic. I urge you to look at this if you want to verify the answer, but the depletion force then comes down to minus del g by del g exclusion by the distance derivative, partial derivative, which becomes minus pressure times pi r plus r square minus d square by 4. And so P, which is n times kBt, and n, which is n by v box, and distance is 2r, and distance is d, which is greater than 2r, which is the hard shell radius, meaning to say the sum of the radii of the two objects, that the distance cannot be less than that, the particles can't intersect, but in this arithmetic that also cannot exceed r plus r. It becomes uninteresting. So depletion measurements like this were made in experiments to find out whether this is real by calculating the free energy for increasing concentrations of DNA from top to bottom, from 5 micrograms per ml to 25 micrograms per ml, showing that the interaction between two beads results in lower and lower free energies of interaction of the beads. So the beads were the ones that were being measured, DNA was the crowded, and the interaction was followed. Uh, Entropic ordering, which was another topic I wanted to maybe just briefly mention, is a further aspect of this, which is that we always talk about entropy as a way to create disorder, but it turns out that entropic ordering also counterintuitively drives indeed the process of order formation at high concentrations. And this is the free energy of it is given by P times V overlap, where spheres are ordered in a system containing filament rods. And these filament rods, in this particular case, that were added were viral filaments, something like tobacco mosaic virus. So, we've talked about volume exclusion, depletion interaction, and now we're going to talk about how polymers are affected by crowding and the Random walk model. And the Random walk model, which we talked about last semester, if you remember, allows for polymers to cross over onto themselves. It ignores, in that sense, self-avoidance. If n is the number of segments and a is the persistence length, then for the size of a macromolecule, is characterized, and the root mean square end-to-end distance is characterized, scales at least, as under root of Na square. But there are competing effects that we know: entropy, which will force the chain to become more compact, and self-avoidance, which will actually force it to become larger and swell it. So if we consider these things, then we probably need to revisit our random walk model for a more realistic scenario, and that involves a so-called self-avoiding random walk, which considers the excluded volume interactions and is based on simple geometric arguments of these rods, where the angle between two rods is theta and a is the persistence length or the minimum rod length. The mutual orientation angle decides the excluded volume, which is given by dA square times sine theta. This is from geometry. And for d is much less than a, the averaging of sine theta over all orientations gives an estimate of the excluded volume, pi squared d by 2. The free energy of G excluded is kb times dn phi. And for n hard cylinders, hard meaning they can't pass through each other, from Onsager's approach, you can get a closed form solution for the packing density as a function of r being n times this sort of complex looking geometric expression, which simplifies to n a squared d upon 8r. And the free energy difference between the RA random walk model and the self-avoiding walk is such that the radius of the fluoride radius, unlike the uh, characteristic random walk radius, scales as a function of n to the power 3 by 5, n being the number of segments with the prefactor that is determined by a and d. So just let's remind ourselves what were a and d. A was our single rod length, minimal rod length, which we call the persistence length, and d is the diameter, the thickness of this. So in a way, a parameter that we had not considered so far in the random walk formalisms that we had been looking at. So random walk versus self-avoiding random walk means that while the random walk scales as n to the power half or under root of n, self-avoiding walk scales as the fifth power and the third root of n. For short polymers, random walk is still valid. For long polymers, this begins to break down. And this becomes relevant when we start looking at some of the more complex phenomena like protein folding in the presence of crowdants, where denaturation and refolding of a protein in a dilute solution does not result in the same processes that it results in a concentrated solution, where aggregation can result. And this becomes relevant when we then indeed talk about protein folding. And this was the last figure in McGuffey and Alcock, and I encourage you to look at it. I might have a chance to discuss it in one of the live sessions. Uh, it's not that important. Just suffice to say that when proteins are in vivo and they are folding, it is not at all surprising that they are in a concentrated solution. So, what prevents aggregation? And the answer to that question is basically chaperones, or you could argue in a sort of biologist's perspective of why do chaperones exist? Well, because at concentrated solutions, proteins when they're folding tend to aggregate, and keeping them apart, allowing for folding in a manner that is consistent with the structure that one would hope to achieve is important. The last bit, I want to talk about diffusion in crowded environments. And again, like in the railway station and railway train entry analogy of the Bombay local, if a particle already occupies a space, then the probability of hopping left or right is now scaled by the volume fraction occupied by the crowded. In other words, if that volume fraction is, let us say, half, then you're multiplying 0.5 by 0.5. And this is what makes things a little more interesting. And therefore, diffusion in crowded environments then becomes a square p right plus a square p left plus 0 p stay, a square 1 minus phi, which effectively means that after n steps, n, which is d by tau, and n msd, n times larger, becomes n times larger, and the diffusion coefficient for a random walker becomes d naught, which is your so-called dilute limit or no crowded condition, multiplied by 1 minus phi, or and d naught is a squared by 2 tau, which is our definition, 1 by 2 a squared by tau, as we have used. The mean square displacement, in fact, then becomes a square by tau, which is d upon 2, or half d, I'm sorry, 2 dt, times 1 minus phi. Yeah, minus t. So, proof, is there any proof for all this? Well, if you now look at the natural log of the diffusion coefficient measured, the effective diffusion coefficient, by the optimal diffusion coefficient, the ideal diffusion coefficient, then you find that they follow a trend that fits this expression. This is a slightly scary looking one with a bunch of constants, but it effectively implies that as the concentration increases, the diffusion coefficient goes down. We talked, when we talked about diffusion earlier, we emphasized the fact that it is a constant and it is a physical reality and you can measure it, and it is true. But when you have concentrations of crowdents which now begin to resemble what we see inside a cell, things get very strange. So this is another way of saying that we have to keep in mind whenever we make these measurements inside cells, a lot more is going on. And this is really proof of that. The expression was fit by Muramutsu and Minton in 1988, and this is what the equation looks like. In fact, self-diffusion and crowding tells you that in addition to other things crowding, you can also have self-diffusive, in other words, self-crowding. Higher concentrations of the molecule that you're looking at result in lower diffusion coefficients of the material itself. So in summary, we have talked a bit about the role of binding probability under the influence of crowdings in a ligand receptor system. We talked about two kinds of situations there. One where the crowdent and the ligand are of the same size versus one where there's an offset, a ratio between the crowdent size and the ligand size. And we got two expressions for probability. I would like you to go back and look at them. We then talked about how osmotic pressure depends on crowding. We delved a little bit into excluded volume interactions, entropic ordering due to viral rods, for which there's some experimental evidence. The theory is a bit trickier. Self-avoiding walks, which gives you a different scaling of polymers if you consider volume exclusion in a random walk polymer. And we talked very briefly about how it might influence protein folding and the need for chaperones. And finally, we ended with diffusion in a crowded environment. So for the next set of lectures, I'm going to talk to you about rate equations in cellular dynamics and how they relate to cytoskeleton polymerization, molecular motors, and the biophysics of development. And that will complete this course. Thank you very much.